transition, if it's a continuous phase transition, they are exponent, and the exponent belong to a power law. For instance, specific heat, correlation length, or magnetic susceptibility, they all follow a power law. Okay, so this is a professor in Cornell. So he proposed that all the cracking noise, okay, of different power law, they belong to a universality. Okay, but in 中文就是有讲跟没讲一样，这样你是说是 university， 但为什么会 university， 他也没讲。那你说啊这种屁话，你是讲这种有什么样 ？It appears in nature. Okay, and up to yesterday, it has been hit something like 700 times, been cited more than 700 times. Okay, so people buy it. Okay, but it didn't really say anything. It just said, they probably belong to a universality class. But why? It says shut up. Okay, I don't know. Okay, right. Okay, anyway, so that's number 2 theory. And number 3 theory is that they are fractal. Okay, because fractal, for instance, a leaf. Okay, oops. Okay, you can see it exhibits a property called self-affinity. 自我相似，对吗? Self-affinity. That means if you look at a big structure, okay, in here, that would manifest itself in a smaller structure, so on and so forth. Okay, or for in this case, they are all triangle, large, medium, small. Okay, that's called fractal. And fractal also exhibit a power law. Okay, and if you want to know why, you can ask Pang Ling. Okay, Pang Ling in this department, he's doing a surface growth. In surface growth, the roughness has 2 exponents. Okay, so that's also a power law. So that's Mandelbrot. Okay, the main pioneer for Mandelbrot. Okay, so he said probably why there are so many power laws because they are all fractal. Okay, so here is his book. Okay. Also, it says the nature. Question? Right. And there are other theory. Okay, some theory they attempt to explain partially. Okay, and some attempt to explain just one power law. And so, for instance, that's in nature communication. That's just last year. Okay, so that's one that says it's a stochastic and something like a ship. Okay, and that's a Stanley. Okay, and it's where it's a Nature paper. Okay, so it's his own theory, and that he used that theory to explain the stock market fluctuation. Okay, so he's less ambitious, but nevertheless, it still go on a nature because it concerns your pocket. Okay, so people love it. Right, question. Right, okay. They are critic on this kind of power law. So, for instance, this is an English lady in MIT. So, I have a paper published by a senior student, Bai Wubin. So Keller is Bai Wubin's supervisor. Okay, and he's a biologist. Okay, biophysicist. So he says the power law probably they are no big deal. Okay, anyway, he says 就唱衰，可以吗？他说 that's no big deal. Okay, so they are critic. Sorry, I'm using slang in Chinese, so it's very hard to translate. Okay, and that's science paper. So they're a group of Israeli. They try to attack. They say is the natural a lot of power law in nature are they really fractal? So they write a science paper, and so Mandelbrot, who is the father of fractal, he wrote a letter to reply. It says, "Shut up, okay? I'm more senior. Trust me, okay?" And then they write back. So back and forth in nature and in science, okay? In 1998, but he died probably I don't know 5 or 6 years probably out of anger. Come on, so it can be okay. So this guy, you can see that the thing I highlight. It says, if you use fractal to explain all the power law in nature, he thinks it's too hasty. Okay? Because a lot of things, they are not really fractal. Because mathematically, fractal has to be self-applied to all order. But there's no such thing in nature. So he thinks it's too sloppy. Okay? So they are critic on power law. But mainly they are criticizing that they are not rigorous enough. Okay? Oops. And that's another paper where, in Science, okay, 3 years ago. So they do a survey. So they take all the power law in the literature more than 100 examples. So the x-axis, so they're not plotting power law. Okay, they're trying to mock, trying to make fun of them. So x-axis is, do they propose a theory? So in this case, they're just talking, blah, blah, blah. In here means they actually have a theory. And y-axis is, do they do a statistical analysis? Okay, in here means they are very rigorous. In here, they are very sloppy. It turned out most of them, they are falling here. They neither have a theory, nor are they rigorous. Okay, so that went to a science server. And here's our take. Okay, so that's our theory. So as you can see from title, we think the power law in complex systems, they are mostly sort of wrong. Okay, because they lost too much information. Okay, so the correct theory shouldn't be a power law. And how do we know that? So we have to argue from information theory. So for this work, we collaborate with Professor Xu. So that's from the Institute of Statistics. So from statistics point of view, we study this work. So you ask me, I'm a physicist, how do I know statistics? So the answer is no, I don't know. Okay, so I rely on my collaborator. Okay, and if you say, okay, if they know, then why didn't they publish? It turned out that people from statistics, they're not interested in this kind. They never read Nature. They never read science. Okay, they don't read literature. Okay, so they do not know about this power law relation. So that's one thing about sort of interdiscipline. Okay, each discipline has their blind spot. Okay, so if you try to cross over to talk to field or other group, sometimes you'll find something very trivial for you, but they didn't know. But they know something that you can make use of. So that's okay. So that's that. So I will not bother you with how they do in statistics, how they measure the information. So I just give you a simple. Okay. So for instance, for this case, so previous people said, the noise. So small noise, medium noise, noisy noise. It looked like a power law, just like earthquake. So that's here. Okay, including Cessna, we proposed the universality for cracking noise. We got more than 700 hits. Okay, that's Cessna. So that, yeah, they've done that. Okay, and as I said, why this is interesting. Okay, people have also do experiment on all kinds of material. So in here they crumple paper, but there are people breaking wood. Okay, so that also causes a fracture. Okay, or breaking rocks or concrete or charcoal. Okay, you think so 有什么这么无聊？可能吃饱饭没事干去弄这些。So I'll show you why. They are all physicists. So for wood, see PRL. Okay, for rocks, again PRL. And how do they explain that? So in this case, they say it's a phenomenon, it's a critical phenomenon, just like phase transition. Okay, and for this guy, he says it's a centile, SOC. For concrete, again, PRL. For charcoal, it's this year, about 6 months ago, 5 months ago. Okay, so people keep starting pumping out when they change the material, they get a PRL. So you can see people are very interested in it. They don't have a theory. They just said it looked like, so in this case, it looked like a standpile. So it's like a SOC. He said, don't ask me why, because it looked like that. And ask Babak. When you try to ask Babak, he's dead. So case closed, okay? Oh shit, oh, sorry. Okay, so that's the situation. So people try to fracture all kinds of material. And one reason it's interesting is because it looked like earthquake, and people are interested in earthquake. So they try to get some insight, okay? But the theories there's no consensus on the theory, okay? Question? They're all physicists, right? Okay. Okay, right, so here's our work. So as I said, different material, when you crumple them, and you log prop, so that's log energy, log numbers of time, it all look very straight. And people say it's a power law. So initially we said, okay, that's a power law. And what about that? You said, it's the same. It's also a power law. But what is that? That is this. this data are obtained by doing this. So I'm crumpling these two materials with two separate hands. Okay, so apparently the sound you record shouldn't be a power law because this guy has a different exponent from this guy. So you have a mixture of two different power. So it shouldn't be a power law. But when you plot the data, it just looks like hell. It looks like straight line. Okay, and if you check the deviation of the exponent, it turned out to be even smaller than individual one. So previous people would say, this is a better power law than individual one, but no, it's wrong. So you know something seriously wrong, okay? You see, the deviation of the exponent is something like 0.010. I'll show you. If you do an individual one, so it's bigger. So that means if these are pure power law, when you do this, you expect them not to be power law, but you get fooled. If you look at the deviation of exponent, you got cheated, okay? Because that's very small, but you know it shouldn't be a power law, okay? So that means in the previous literature, for the 100 instances, people are using that. So that's process are your data. So you just plot it and they just measure the deviation. And when the deviation of the exponent is much smaller, let's say 1 or 2 orders smaller than the exponent, they say it's a good power law. But so we have proved that you need to be more careful than that. Okay, so that's the motivation. Okay, question? So that's one key thing that I want you to learn. You shouldn't trust the deviation of the exponent. Okay, that would cheat you, as in this case, because they are being crumpled separately. So there shouldn't be a power law, but it has a small deviation. Okay, so we have to rely on a better method to distinguish. Okay, in this case. Question? Yes.
Excuse me. So the slope of the separately crumpled.
The slope. Okay. Yeah.
Yeah, but I mean, if together, and the slope will also look like this or different.
Yeah, of course, it has a slope. So slope will be something like a 数学平均. But the point is, in previous worker, they would check the deviation of the slope. If the deviation is much smaller than the slope, they would say it's a good straight line. In other words, they would say it's a power law. And using the same criteria, they published 100 papers. As I have just shown you, the shock, the forest fire, the zip law, okay, they all based on this criteria. But I just do a simple experiment. I told you there's a pitfall. Okay, you need to be careful. Okay, so how careful? So I have to ask my statistics friend. Okay, so he says that. Okay, so that's a reason. Okay, give you a rough idea. So the deviation of the exponent apparently it has no dimension. Okay, but the standard deviation has a dimension. So the definition of this is that. So when you crumple two things, you don't expect it to be power law. So if you fit the data by a power law, apparently the deviation, 就是标准差 will be very large. And you said, if this is large, how come this becomes small? It turned out that the curvature is even bigger. So that gives you the delusion. Okay, so that gives you a delusion. And we checked that in real experiment, that's the case. Okay, so that's why you shouldn't trust a small delta beta as a sufficient condition for power law. Okay, and that's that. So this is what our statistic friend tells us. There's a sort of a criteria called AIC. It's sort of 101， 就在他们那边有点像 holiday 里面的，不骗你，可以吗？在统计学里面，这是像 holiday 里面的，是每个人都知道。It's called AIC. So what is AIC? It tells you. It said you calculate this thing. Okay. So what is that? It's called AIC value. So L is something like standard deviation. So if you use standard deviation, so that will be that. So standard deviation is here. So when you have a set of data, and you try to fit them by a model, by a function, you can calculate the standard deviation. So apparently, if your model contains more tuning parameter, the standard deviation can come down. Okay? 就是你拟合的参数越多，你拟合的越好，so the standard deviation will get smaller. But there's no limit. You can use 100 fitting parameter, but it's meaningless. Okay? So in statistics, so people use this. So that will be the standard deviation. And K is the tuning parameter. So that means if you use 100 tuning parameter, this guy will be small, but this guy will be large. So you need to optimize between these tuning parameters, that's sort of the neatness of your model. And this is the accuracy. You need to compromise. And as you see, this is very resemble to the Helmholtz free energy in physics. You need to compromise between internal energy and entropy. So it's very similar, okay? Okay, don't ask me 你再问我就破功了哈，可以吧？这个我也是现学现卖，可以吧？反正他们说这个 ，OK。All right, don't ask me any detail because I will not answer because I don't know. That's what my statistics friend tells us. So using that, and they are even more, all these are statistical jargons. Anyway, I put on this just to make you look like they are very, very complicated and very rigorous. Okay. Likelihood ratio test. 我不知道有听过这个举手。哦，哎，你很强，你在哪里听过？你怎么会用过这个？你什么时候学的？啊？你是研究所学的吗？对啊，因为跟我们合作的科大的学生，他们说大二就学过这个，很强啊。大陆科大的，他们大二那个实验课就要学这个，所以我觉得很强，知道。Okay, so we have a bunch of statistical criteria. So I just show the result. Okay, so it turned out. Okay, let me show you that. Okay, in here we check 8 examples, which I have shown you, famous power law. Okay, so I will check with a simple power law. So that's what they claim, and this is double power law, and this is called a shifted power law. So shifted power law means instead of this, it looks like that. Okay, so we just check the AIC value for simple power law, and that's a double term, and that's a different power law, and all the examples. Okay, so the bolded phase means they are, according to the statistics, they are better. Okay, they are better. So for the first 2 cases, double power law is better than the power law, and for the last 4 examples, the shifted power law are better than simple power law. So you can see all these are Nature and Science paper, okay? And according to a rigorous statistics, they are not the best model. So, okay, so according to statistics, that means if you use a power law, you're losing too much information, okay? Too much information. A different fitting function is better, okay? And you will ask, so what? Okay, for instance, for earthquake, so the original simple power law is the dotted line. And according to statistics, the double power law, the red line, is better. And as you can see, they're almost the same, but they deviate in large earthquake. So that means if you trust statistics, that means current prediction of big earthquake is underestimated. It's underestimation, okay? Okay, because this one is higher, okay? So that means a more accurate fitting function can give you a better prediction. And as far as earthquake is concerned, that has something to do with human life. And for stock market, that has something to do with your property and your money, okay? So we think that's important. Okay, question? So that's power law. And if you want to learn the method, you can read our paper or you can check Wikipedia, okay? It's called AIC. Question? All right, okay, so we have model. We have model to explain why crumbling. Okay, that's. Okay, so let me give you another interesting. So that's another reason why we think it's a nice paper. Right, okay, so our students, they proposed an experiment. He said, if you crumple them separately, you expect them to be not a power law, but 2 power law, okay? But what if you crumple them together? Initially, they are just interact loosely. So you expect it's still a double power law. But as I just said, when you crumble it real hard, it turned out using the statistical method, it becomes a power law, a real power law. Okay, it may look trivial to you, but it's very, very important in 3 aspects. Okay, the first aspect is, in this case, it's the first demonstration in all complex systems. People have long suspected that interaction can tune the statistical behavior of a system. So in this case, when the interaction between these two things is small, it behaves like a double power law. But when the interaction enhances, it changes behavior. Okay? So that's a neat demonstration that interaction, magnitude interaction, can change your statistic. Okay? And the second thing is, in this case, it demonstrates that eventually it looks like a power law, but it can evolve from a double power law. So that means double power law and simple power law, they are very close. They are in close vicinity in the phase space. No? No excitement. Okay, but anyway, but that's I forgot the third point, so don't ask me. But anyway, it turned out to be a very important complex system. So that's it. Okay, so maybe I should go. So in the forget about that. All right. Okay, so let's go to chopsticks. So chopsticks. So in this case, chopsticks. The sample we use are chopsticks and spaghetti. So it's a strange mixture. Okay, chopsticks is Oriental, spaghetti is Western. You don't eat spaghetti, right? In India, no. But you do use chopstick, right? Okay, so that's that. Okay. So that has been accepted by PRL. Okay. And why is that interesting? So, firstly, why do we want to mix these two materials? So we can look at the cross section. They look very similar. Okay. See, in chopsticks, the cross section is called vascular bundle. Okay. So you take a bundle of spaghetti, it looks very similar. And it turned out when you break them, the noise they emit are very similar. Not just to the, so I already told you that in earthquake, the most important law is called a Richard GR law. But there are number 2 law and number 3 law. Okay? For crumble paper, you only get number 1 law. But in this case, all 3 law in earthquake, you can find it in chopsticks and spaghetti. Okay, so that is very special. Okay, and here comes the experiment time. So if you want to try it, you can pass it on, and don't break it yet. don't break it as yet. Okay. 是不是穿一点？我拿一把，我到旁边。So we have, for this experiment, we probably had break, I don't know, 10,000 chopsticks, okay. But the experiment doesn't always succeed. The reason is, it's hard to say. In 中文，这中文有那个结，有结就嘣一下就断掉，那个结叫什么 ？Node. If your chopstick happen to have a node, it doesn't work. You just snap. Like this. This is from NTU campus. Okay, if you break it, you just get one sound. Just one sound. You get one sound. You get one sound, okay? Okay, now the interesting part. There are 5 chalks, okay? If you record the sound, see, you probably get 10 sound. Okay, anyone want to explain a theory? You have heard it, right? It's more than 5. Okay, you can hit the sound. So that's one puzzle. And the other thing is, if there's no note, that would be good. if you do it real slowly, you get about 400 sounds. If you do it real slowly. Okay, so the first question is why? Why is this so different from this, and spaghetti? Now, anyone venture a guess? What's special about this guy? Okay. Okay, so that's the fun of this talk. Okay, so you can try. Okay, so it's very special. It's very special. Now you want to ask why this is special, and once you ask that, then you go on to ask, does that have any bearing on the real earthquake? Okay, and why is that? Let me show you. In real earthquake, because so this is the first paper that so as you know, when you write a paper, you would put it on the archive, okay, and it takes forever before it's published. So the first week when you submit it to the archive, so we get a lot of letters, so including this guy. So I don't know. So they start to report the work. So probably they're very interested in the spaghetti, because in Western, when they eat spaghetti, they need to break it, okay. So we know that that action has to do with earthquake. Okay, they got panic. Okay. Right. Okay. So this is another thing that links spaghetti with earthquake. So this is something in Canada. Okay, it's a competition. You try to build a structure with spaghetti, and once you build that, so you have different team, and the judge will come and break and try to shake your desk, and if it doesn't fall, then it will enter, and then they will try to measure which one is the tallest. Again, that would win the champion. Okay, so that's the only thing. If you type spaghetti and earthquake, that's the first hit you get. Okay, but if our paper got published, so probably our paper will be as popular as that. Okay, right. So that's spaghetti and earthquake. Okay, right. Oh, okay. You again forgot that. So initially, I put on the referee report just in case if there are any one of you that are troubled, that are sort of saddened by the referee report, I'll show you that. Okay. I'll show you just a glimpse. So we have 4 referees, and one referee was the meanest. And let me show you how mean. You probably want to jump from upstairs. Let me show you the meanest one. Okay. The meanest one. This one. This manuscript is just high school. Okay. And I hate, because I already spent too much time refereeing this paper. Please stop sending that to me, okay? So that's a meanest. Don't tell me you get anything worse than that, okay? So that's meanest, okay? So for this work, 3 referees love it to death, but this guy hated it to death, okay? So this try to, instead of criticizing us, he tried to criticize. He said, there's a moron. One of the referees is a moron. Okay, so adequate incompetence of the other guy. So the other 3 guys, they are morons, and so they try to attack each other instead of attacking us. So it's very fun. Okay, all right. Okay. Anyway, the story is closed, so we got past. Okay, right. So that's a machine. So you don't want to write the PRL paper saying your machine are 2 hands. Okay, that will not get published, so you need to build a machine. But actually, if you do a hand, use your hand, the result are the same. But you try to make it scientific. So you build a sort of a breaking bamboo machine, okay? So that's making it more scientific, but actually it's a bullshit. Okay, it's a machine, okay? You can just use your hand, okay? And so that's so now you can break it and try to observe it. So I'll give you 30 seconds. If you can see any unusual when you break. See? You can see the double-headed yellow line. So what does that say? That means initially, before any fiber break, the chopstick is about 20 centimeters. But when it starts breaking, you can see in this segment, they are almost straight. In this segment, they're almost straight. But this part, only this part is bended. That means there's the effective